Lesson 2 is our second of 2 lessons on number, and it's the first of 10 major concepts that we'll discuss in this introductory 25 lessons to Shormann Algebra 2. And so let's look at part A on special number types, and let's think about some things here. Do you believe God made numbers and uses them to bring us joy? Well, I do. We do in our company. So I know math isn't everybody's favorite subject, but give it a break a little bit. I'm sure there's been a time when a number fascinated you, such as when the time was 12:34 p.m., like 1, 2, 3, 4. Or the number on your basketball jersey was the same as the number of your favorite professional player. Or in the calendar date, March 14th, 2015, 3/14/15, that matches the first 4 digits of pi, 3.1415. And March 14th happens to also be celebrated internationally as Pi Day. So in this lesson, we're going to review and introduce some new number types that you'll use in almost every lesson. Other types will be used less frequently, if at all, but they're just interesting to know about. So don't be afraid to let numbers bring you a little joy. Remember the general grouchiness we talked about avoiding back in lesson 1? Don't be that way with your math course. So first, let's look at factorial and triangular numbers. You should have already looked at your rules and definitions, seen what factorial means, seen what triangular numbers are. So we're just applying what you learned in that right now. So a common use of factorials, that's when working with probability-related problems like permutations and combinations. You'll learn about those in lesson 81. Triangular numbers, those are also used in counting type problems. Triangular numbers, they get their name from the fact that you can create an equilateral triangle from them. There's various interesting examples of triangular numbers. One of them is the number 153. T to the 17 equals 153. So that's that triangle shown below. It has 17 dots on each outside edge, and this number 153, it actually appears in Scripture, John 21:11. And Jesus commands Peter to cast his nets one more time after a fishless night. This time he pulls up exactly 153 fish. Now, in doing some brief research on this, no one knows for sure what the significance of exactly 153 fish is, as far as I can tell. The great theologian Augustine, he understood the 153 as the triangular of 17. He suggested the catch was representative of 7 spiritual gifts plus the 10 commandments. Reverend James Jordan, he says it represents the completeness of the gospel in spreading to all nations, and 153 symbolizes the number of nations that will exist in the new creation. So whatever the reason for this number, we can be confident God had a very specific purpose for using it in this verse, although our human minds may never fully understand its significance this side of heaven. That it is a triangular number, that it relates to symmetry and perfection, like in that triangle, equilateral triangle, and possibly to other important numbers in Scripture, that does attest to the purpose of why there were 153 fish and not 154 or some other number. Let's go ahead and do an example now. Let's evaluate the factorial and the triangular for those 3 different numbers. So let's do A first. And so 5 factorial, that would just be 5 times 4 times 3 times 2 times 1. And 5 times 4 is 20, 3 times 2 is 6, times 1 would just be 6, so that's 20 times 6 is equal to 120. And then the triangular of that, we could just say T subscript 5, and that would be 5 plus 4 plus 3 plus 2 plus 1. Do you see the difference here? The factorial, they're all times each other. The triangular, they're all added together. They're all plus each other. And so adding that together, that would give us 15 for the triangular. So once you pause the lecture and see if you can do B on your own. So for the factorial, we'd be doing 6 factorial. And I'm not going to write all of that out, and you can use your calculator on these, because the goal is not to see if you know how to do multiplication, but do you understand what factorial means, what it's asking you to do. So you can use your calculator, and look at this calculator on a Macintosh computer. It already has a factorial over there on the left. So you just type in 6, hit that factorial button, there's your number, 720. For the triangular t of 6, you'll have to add those together, and that will give you 21. Let's see if you could do C now on your own. So for C, 7 factorial and the triangular of 7. So again, we can just do that on the calculator for the factorial. 7 exclamation point 5040 for an answer there. And then the triangular t of 7, you just need to add those together, 7 plus 6 plus 5 and so on. You might even notice that t of 7 is equal to t of 6, which you already calculated, plus 7. So it's equal to 21 plus 7 is 28. Let's look at some other special number types, square roots and other fractional exponents. And looking at a little history again here, the Greeks, they did much to develop mathematics in the centuries before Christ. Most of them were not Jewish at the time, or after Christ came, trusted Christ as their Savior. Their unbiblical views, those gave them inaccurate views of time. They had a cyclical view of time. They thought it was eternal, that it went on and on forever, but that it just went around, it just repeated itself in a circular, cyclical pattern. And they shied away from accepting thought-provoking realities, things that are hard to understand but are real, like infinity or eternity. The Bible talks a lot about eternity. Like irrational numbers, which don't make a whole lot of sense sometimes, that the decimal pattern repeats or doesn't repeat itself. And we'll talk about those more in lesson 3. But their timidity towards those kinds of things, that help stifle the progress in math and science. Interestingly, it wasn't until Christians rejected their unbiblical views, instead of just repeating them over and over for 2,000 years, they rejected them during the Reformation, and humans' understanding of math and science, then it began to progress again. So the Bible, it describes time as linear and eternal, not cyclical. Christians, they don't have any problem with the reality of infinity, with 1, then 2, then 3, then 4, and so on and so on and so on forever. Many scholars also believe the Greeks' inability to accept irrational numbers, that's what led them to focus more on geometry than arithmetic. When they did geometry, they didn't even have any measurement tools. They just had a drawing compass to draw circles with, and so that has a point on one end and a pencil on the other, and they could draw circles with that. And then they would have a straight edge that would just help them draw straight lines that they didn't know the measurement of. A lot of what they learned has been helpful to us, for sure. But here's something that was a problem for them. Look at that square that I have drawn on the left. It has sides that are 1 unit in length. Now the Greeks, they could draw squares using their compass and straight edge. They didn't measure them, because what happened was that, like this triangle or this rectangle, you can see the triangle that's formed there, and that diagonal that goes across there, it happens to have a side equal to the square root of 2. That's what the diagonal equals. That's an irrational number. Like pi is an irrational number. There's simply no way to write the square root of 2 as a ratio of integers, of non-decimal numbers. So the Greeks, they could draw a square perfectly, or as close to perfect as possible, but they kind of covered up the fact that they couldn't find the exact value of a very simple square with sides of length 1. See, they worshipped human reason instead of worshiping God, because they worshipped human reason. If they couldn't understand it, then they just rejected it or ignored that. But a square has to have a diagonal, right? It's a very real thing that it's equal to the square root of 2. Christians, we don't have a problem that we don't understand the exact value of that. That's okay. So while we're on that topic of square roots, let's go ahead and practice some problems where we simplify square roots. So if you don't have them memorized already, work on memorizing this table over here of perfect squares. This will help you. So the square root of any perfect square, so any number in the right-hand column, the square root of any of those equals the number in the left-hand column. So the square root of 4, that's equal to 2. If you take the square root of that. Square root of 9, that's equal to 3. Square root of 16, that's equal to 4, and so on. So hopefully you can go both ways with these, all the way down to 13, where 13 squared is 169. Square root of 169 is 13. So let's look at problem A here. And what I like to do on these to simplify things like this, and they're designed for you to be able to simplify them, is to think of two factors. One that you know the square root of, and factor that out first. So in 108, you might want to just get your calculator out, and you could do 108 divided by 4, divided by 9, divided by 16. 108 divided by 36 is 3. So square root of 108, you can break that into the square root of 36 times the square root of 3. The square root of 36 is 6. So you get 6 times the square root of 3. So we factor that into two factors, square root of 36, square root of 3. One of those factors, we know what the square root is. We didn't just do, oh, well, it's 108, so it's even, so 54 times 2, square root of 54 times square root of 2, and then we're like, well, now what do we do? Well, I could break the square root of 54 up again, and you could do it that way. But that's just not very efficient to do it that way. And it's a lot easier to think of a factor that you know the square root of and factor that out. So look at B, the square root of 245. So again, it's a good idea just to get your calculator out on these, and let's think of 245. Well, it ends in 5, so maybe 25 works. We could do divided by 25, and well, no, that equals 9.8. That doesn't work. So let's think of something else there. Well, 9 times 5 is 45 in that 245. So maybe 245 divided by 9. Well, no, that doesn't work. How about 245 divided by 49? Oh, well, that equals 5. And the square root of 49 is 7, right? So we can say the square root of 49 times the square root of 5 is equal to 7 times the square root of 5. So there it is. 7 times the square root of 5. We simplified that. C, the square root of 486. So again, just get that calculator out and think of two numbers, one of them that you know the square root of. So one of those perfect squares, divide by that. And you may have to do several of them, but if you did 81, 486 divided by 81, well, that equals 6. And so we could break it into square root of 81 times the square root of 6. Square root of 81 is 9. 9 times the square root of 6. That's what that simplifies to. And that's what we mean when we see a problem like this and it asks us to simplify and it's just a square root of a number. It means to break it into factors that we know the square root of. It's not like it's bad to leave it as square root of 486. It's just not the standard form. The standard form is to factor out any factors that you know the square root of that are perfect squares. Factor out the perfect squares. So all we've been doing here is just applying that product of square roots rule from the rules at the beginning of lesson 2. Let's do another one. Find the roots of the following numbers here. And so here we're thinking about square root and that definition of square root and just what that square root symbol means. And so in your definitions you had the symbol there, the radical sign with an N there and X. that is the same thing. It's shorthand for writing x to the 1 over n power. So in A, what we're really saying there is 8 to the 1/3 power. What is 8 to the 1/3 power? When you see just a square root sign like the square root of x, that's x to the 1/2. It's understood that means x to the 1/2 power. But if there's a number in there, then it's to the 1/3, to the 1/4, just whichever. So these are designed to simplify into a simple integer value for a root. So like when we do square root, we're thinking what two numbers that are the same number, what times what, equals what's inside the radical sign. Here we're thinking what three numbers if it's to the 1/3 power. So that'd be 2 times 2 times 2 is 8, right? So 8 to the 1/3 is 2. And so B, that's going to be minus 8 to the 1/3 power. So that's a minus 2, right? Because minus 2 times minus 2 is a positive 4 times another minus 2, that's negative 8. And then C, that one is to the 4th, or the 4th root of 16. So it's like saying 16 to the 1/4 power. And so there we're saying what number multiplied 4 times in a row. It's the same number every time. That would be a 2, right? Because 2 times 2 is 4, times another 2 times 2, that's 4. 4 times 4 is 16. So that'd be a positive 2. So hopefully that was a review for you. So lastly, in part A, let's look at imaginary numbers. And you might want to review the definitions for square roots and for complex numbers listed at the beginning of the lesson. So if you have the square root of x, that value squared, then that equals x. Then think about, instead of x in there, you had square root of minus 1. Well, square root of minus 1, that squared is equal to minus 1. And then for shorthand, we say that the square root of minus 1 is I, which means I squared is negative 1. So instead of writing the square root of negative 1 over and over and over again, Leonhard Euler, he decided to just use the letter I. Wasn't used that much in mathematics, so let's just use the letter I and place a square root of minus 1. It's easier, faster to complete lengthy handwritten calculations. Remember back in his day they did everything by hand pretty much, so doing things in that way was a lot more efficient by making square root of negative 1 I. So Euler, he was a Christian man, considered the greatest mathematician ever, and many of the symbols he developed hundreds of years ago like this, they're still used today. So here's something to think about. I hope that you're comfortable doing the simplifying square roots of perfect squares, like the square root of 16 is 4, square root of 49 is 7, stuff like that. But how do you simplify the square root of negative 1? You know, if it's the square root of 49, we think what two numbers, what times what, equals 49. Well, what two numbers multiplied together equal a negative 1? Well, there's nothing that works. I mean, you might have said, oh, well, minus 1 times 1. But no, those are opposites. Those aren't the same number. It has to be the same number. What two numbers that are the same multiplied together equal negative 1? So there's no real number that fits that. That's why we call this an imaginary number. So you actually use these in science and engineering, and you may have a course that you're doing where negative values can be measured, like in a system with alternating or AC electrical current. Sometimes those systems have complex numbers. They have a real part, usually referred to as A, and then an imaginary part referred to as B, then times the square root of negative 1 times I. That's the imaginary part. Something to think about is that any real number is also a complex number, right? It just has a B value equal to 0, so the BI part is just not there. So let's do some more simplifying. Simplify these. Square root of negative 11. So the simplified form of that means we don't have a negative under the square root symbol. So we have to factor. And so what that means is for a, we'd have to say the square root of 11 times the square root of negative 1. Factor out a negative 1. And then square root of negative 1 is I, so we would just write this simplified form as the square root of 11i. And so that would be our answer, square root of 11i. Then in B, again, if we see a negative inside a square root sign, that's the first thing we should want to do is get that factored out. So we have square root of 108 times the square root of negative 1. So we know that square root of negative 1 is going to be I. We already did the square root of 108. That's square root of 36 times square root of 3, or 6 times the square root of 3. Times the square root of negative 1 would just be an I on the outside of the square root sign, though, right? So you got to make sure and write it on the outside of the square root sign. And then C, 14 times I squared. Well, look over here on the left, if I is equal to the square root of negative 1, then I squared, that equals negative 1. So we also have that written right up here. I squared is equal to negative 1. So what we're really saying there in that problem, to simplify it, we just say 14 times negative 1 is negative 14. And so that would be our simplified form. Moving on to part B on arithmetic operations. You might want to refer to Shormann Algebra 1, Lesson 2. If you need to review basic addition, subtraction, multiplication, division, algorithms, I'm not going to go into that a whole lot here. Here we're going to review and apply the commutative, the associative, the distributive properties to simplify some basic numerical operations. So let's go ahead and get started with A. So when you see like a 4 minus 6 or a 6 minus 1, instead of subtracting, think of adding negative numbers. Use the associative property to help you group things in pairs. And also the absolute value of 7, that's just 7. So we can say minus 2, just rewrite this, plus 4, minus 6, minus 1, plus 7. And so let's add in pairs here. Let's add the minus 2 and the 4, the minus 6 and the minus 1, and then we have that 7 on the end that we don't want to forget. So minus 2 plus 4 is a 2. Minus 6 minus 1 is a negative 7 plus a 7. So hopefully you can see minus 7 plus 7, that pair, that would go to 0. And so we just end up with 2 for a simplified form of that expression. Now B, we need to use the distributive property to expand that. So we need to take that 3 times the square root of 2, and we multiply that by the square root of 2 on the inside. Then we take it and multiply it by the 4 times the square root of 5, putting a plus sign in between. So we have 3 times the square root of 2 times the square root of 2 plus, because of that plus sign, 3 times the square root of 2 times 4 times the square root of 5. And now let's keep simplifying. Now square root of 2 times square root of 2, that's just going to equal 2, right? Because that'd be the square root of 4, and the square root of 4 is just 2. So it'd be 3 times 2. And then we have 3 times 4. Let's do the things that aren't square roots. And remember, order doesn't matter in multiplication. All these terms are multiplied together. So we can rearrange them. 3 times 4 is 12 times square root of 2, square root of 5. That'd be square root of 10. And that's not going to simplify anymore. So we're just left with 6 plus 12 square root 10. That's our simplified form. And then C, what we want to do on a problem like this is all those I squareds, we want to make those negative 1. So we have, let's do that first. We'd have 6I parentheses negative 1 minus 5 plus 2I. So that's equal to 6I times negative 6 plus 2I. And so expanding that out, we'd get negative 36, because 6 times 6 is 36, negative 36i. And then 6i times 2i would be 12i times I, or 12i squared. But I squared is just negative 1. So we end up with minus 12, because it's 12 times negative 1 is minus 12 minus 36i. Normally we write the real part first and the imaginary part second. So that's that standard form of a plus bi that we talked about earlier, and it's also in your definition of a complex number. Let's finish up lesson 2 with exponents and logarithms. Those will be in lesson 3. Those are related to each other. If you did Shormann Algebra 1, you did logarithms towards the end. But logarithm means exponent. We'll talk about that more in the next lesson. Both of these are ways to simplify the writing of very large and very small quantities. That's one of their main uses. Now, modern exponential notation, that was developed by René Descartes, and he published his method in 1637. So it's been around a while. There's actually many forms used to describe exponents at the time, but Descartes was the most efficient. It was deemed the most efficient. And astronomers like Johannes Kepler, they were particularly interested in finding simpler ways to work with extremely large distances and sizes they were discovering in astronomy. Remember, we talked about Kepler a little bit in lesson 1. He was a Christian. He was also a math teacher, and he used Roman numerals for exponents. So where Descartes, he might express an exponential term as, like, for example, 3x squared, Kepler would have written it like this, 3 with a Roman numeral 2. He'd leave the reader to assume the presence of the x variable, and that worked well unless you really did mean 3 squared or 9, so that would be confusing. So think about the early 1600s. Paper was a whole lot more expensive back then. They didn't have typewriters or computers. There was a constant pursuit then to find ways to write as much as possible, as efficiently as possible, in as little space as possible. So let's go ahead and review some concepts about exponents now, and this was hopefully in your Algebra 1 courses, definitely in Shormann Algebra 1. And so simplifying these to eliminate all unnecessary exponents. So just taking a look at a there, we see 6 squared over 6 squared. Those would cancel. Those factors would cancel. And so a, that simplifies to 6 to the 5th times 7 to the 4th power. So when you see simplify to eliminate all unnecessary exponents, that sentence in your homework set, in your practice set, that I don't want you to get a single numerical answer for that. I just want you to get rid of the unnecessary exponents. And so that would be the answer to A. Just leave it like that. So the goal isn't to see if you can multiply that out. It's just to see if you understand how to simplify unnecessary exponents, getting rid of those, using your product and quotient rules for exponents as you need to, as well as commutative and distributive properties to rearrange and expand. So all that to say, B is a little more complex than A. We need to move that 7 to the minus 2 to the numerator. And so let's do that. And we'll have 6 to the 5th. And let's move the 6 squared next to the 6 to the 5th so we can see those similar bases together and how we need to add the exponents eventually. 7 to the 4th, and then move the 7 to the minus 2 up. That means it turns into 7 to the positive 2. So then, similar bases multiply together, add the exponents. That gives us a 6 to the 5 plus 2 is 7, times 7 to the 4 plus 2 is 6. 6 to the 7th power, 7 to the 6th power. We've simplified that to remove all the unnecessary exponents. And then C, we need to expand there using the distributive property. So let's take that 2 to the 3rd over 5 to the 5th, multiply it by the 5 to the minus 3 over 2 first. So we'll have 2 to the 3rd over 5 to the 5th times 5 to the minus 3 over 2. And that's like saying 2 to the 1st power, right? If there's no exponent there, it's understood it's to the 1st power. We can write it in just to remind us of that. then plus, because there's a plus sign between the two terms inside parentheses, 2 to the third over 5 to the fifth times 5 squared over 2 to the third. And so now we're going to cross those out because it's the same thing, right? And the same thing over the same thing, that always equals 1, right? For the rest, though, the terms on the left will have a 2. Move that 1 up, so we'll have a 3 minus 1 times 5 to the minus 3, moving the positive 5 exponent up, so that makes it a negative 5. And then that's going to be plus, I'll just put this down here, 5 to the 2 minus 5. Let's write our final answer over to the left here. 2 to the 3 minus 1, that's just going to be 2 squared, times 5 to the minus 3 minus 5, that would be a 5 to the minus 8. And then plus 5 to the 2 minus 5, that'd be a negative 3. So that's the simplified form. For C, removing all unnecessary exponents. Let's do one more problem with exponents, and this type of problem it looks really simple, especially compared to example 2.6, which was just example 2.6 was about moving those exponents around from numerator to denominator, or vice versa. This problem is a common one that gives students trouble in Algebra 1, so let's make sure you have this down already, you understand this, and we want to write the answer on these as a number without exponents. Okay, so we want to get an actual calculation here. So for A, what we're saying there is that minus, we think of that as the opposite of 3 squared. Well, 3 squared is 9, so the answer is just minus 9. B, we have the opposite of 3 to the minus 2, so we need to make that exponent positive. That means we need to move the 3 to the minus 2 part to the denominator, so we end up with a minus 1 over 3 squared. And so that's going to be equal to minus 1 over 9. We could also write that with the negative out front. We could just call the whole thing negative 1/9. That works as well. For C, look at the difference here between A and C. Both of them have a negative 3. It's just that in C, the negative 3 is inside parentheses. So that's saying to do negative 3 twice. Negative 3 times negative 3. So that answer is a positive 9. That's one of the main places students have trouble with negative signs in Algebra 1, is that right there. Understanding the difference between problem A and problem C. Problem A, the negative is out there by itself. It just means the opposite of all of this, okay? The opposite of 3 squared. So 3 squared is 9. It's saying the opposite of 9, negative 9. C is saying to do minus 3. That's why the parentheses are there. It's saying take that number minus 3 and multiply that twice. So then D, think of B and D. B's just got the minus sign out front. It's saying the opposite of 3 to the minus 2. D is saying to move that to the denominator, make it a 1 over negative 3 parentheses squared. So it's saying 1 over minus 3 times minus 3. That would be a 1 over 9. Okay? So get the opposite result as in B. So hopefully you see how those are similar, but also how they're very different. B and D are opposites of each other. And so are A and C. Okay, well that's all for lesson 2.